Hello, so this is the first part of my review of lecture 19, Determinant and Cofactor. So there are only like two things that are important in this chapter. So the first one is the big formula and the second one is the cofactor. So let's start with the big formula. And let me start with the 2 by 2 example. So there's another way to look at it to how we can arrive at the formula of the determinant, the AD minus BC. So if we use the rule number 3, which are the addition of each row, so we can say this, we can keep the first row fixed first, and we can separate this into 0D and 0, and then we can separate this into two parts, which is, I'm writing the determinant now because I'm ready to use that term, that formula, the property of the third one, which is, let's say I keep so now I'm keeping the second row fixed and I'm changing the first row here, and then the same thing goes here. I'm keeping the second row fixed, right? But I'm changing the first row, and there should be a plus sign here because we add them all. Okay, so what do we have here? So this also has that property of the columns of being 0, so the determinant is 0, and the same goes here. And then we arrive at this property, which is the diagonal, the product of the diagonal. And it's just beautiful to see like how all the properties now come up together and we can use them really well. And this is also using another property, property number 2, which is the, if you reverse the order of row, then you must reverse the sign as well. So let's like have this, and then we reverse the order, and now we can do that product of the diagonal. So this leaves us with the minus of BC. So there you have it, we have this again. And I just want to point out, so we can expand this 2 by 2 matrix into this form, and then we left off with this. And then notice that that term that doesn't give us 0 is the one that has the component, only a single component, and then the 0 for each row and the column. So those with the rows on the column or in the rows will be 0. Their determinant will be 0. So this idea also expands to the 3 by 3 matrix, for example. Now, how about if you have this one right here? Now, eventually you will left off with some kind of matrix that has this, and then, for example, these, and you get the idea. So the point here is that in the end, the term that has the determinant of a non-zero determinant will be the term with like all kinds of the permutation form of all this combination. So how many of them? In case of 3 by 3, you guess it, it's 3 factorial. So in this case, it's 2 factorial. That's why there are 2 terms, 1 and 2, that with the non-zero determinant, and in this case there will be 6 of them. So what are they? Let's see, let me delete all of this first. So now I have it here, the 3 by 3 matrix, and I already also explained how it goes with them briefly, and this is the expansion of them in terms of like there are 6 terms, because they're the 3 factorial and equal to 6 term with non-zero determinant. So let's see how it goes for each of its determinant. So the first one is pretty straightforward, so I will just write it here. The A11, so this is just the products of the diagonal. And for the second one, remember, we can utilize that property number 2. We can switch up between row first and then make them in the really nice form of a diagonal matrix. So how many of a row switch we have to make? First, okay, we have to switch this and this, and then the second we can switch the third and the second. So we have two switch. So remember, first we reverse the sign to the negative, but secondly we also reverse the sign to the positive again. So we have positive sign there, and the same goes for the third one. I'm not gonna write it and explain further, but you can just do it yourself. So let me just write the positive of a of all the term, and then how about this one, the third, the 3, 4, and the 5th? Here you can only need to do one row exchange, which is this and this row, the second and third, to get in the form of the product of the diagonalization. Yeah, just imagine that you move this here, you move this here, so you get this form. So you can pull out all the vector, you get the identity. So don't forget the -1 there. And actually the same goes for this one, only one row switch. So I'll just continue on, and then the same goes for the last one, which in this case you only need to switch between row 3 and the row 1. Okay. And I want to bring out the point, emphasize one thing, is that again you notice that there's only one component here along its column or its row, and there's only one component here along its column or its row, and again the same thing here along its column or its row, and the same goes for all the term here. So don't forget that part. The only term that gives us the non-zero is those that satisfy this properties, and actually that it is. So the formula of the big formula is the oh, that's really weird. The big formula of the determinant was what I want to say is actually the sum of all the determinant of the permutation matrix. So what is this? This is the determinant that governs whether you will have the negative or the plus sign. So you remember we exchange rows, so those will be the thing that decide the negative and or plus, and then we have like all of them. So let us see in this example the alpha. I'm just gonna write what the book also write, and the beta, and until the omega. So this is the formula for what the book also says, the big formula for determinant, and you can see it why you can expand it here. This is the example of 3 by 3. And also there's one thing that I want you to notice, that the half of them, so the 3 of them has the positive sign, 1 to 3, and 3 of them have the negative sign, so minus, minus, minus. So this also applies to n by n matrix. So half will be have the plus and half will be the minus. So that's it for the first part.